So we've been talking about the nucleophilic acyl substitution reaction, and last time we had several different types of nucleophiles that can react via this mechanism to give us substituted carbonyl compounds. There are other nucleophiles that participate in the nucleophilic acyl substitution mechanism, but they undergo substitution twice. And so we want to illustrate this concept in the context of a multi-step synthesis. So let's say we wanted to make this molecule here. So I've got a benzene ring with two methoxy groups paired to one another, but then I have another ring appended to it. We could potentially form this molecule by doing an intramolecular Friedel-Crafts alkylation. So this is not a substitution chemistry quite yet, but that's how we might be able to do that transformation. Now, where the nucleophilic acyl substitution chemistry comes in is in this step. We could potentially make that molecule from a precursor that has a carbonyl. And so the precursor that would have a carbonyl in this case would be the carboxylic acid. And we can make that molecule in a couple of steps from dimethoxy benzene and succinic anhydride. So the real question here is, how would we perform this transformation? Right? How do we take the carboxylic acid and make the dimethylated tertiary alcohol? Well, there are actually two possibilities. And I want to talk about the first possibility first. And this particular sequence, I'll call pathway A, is not exactly the best pathway, and you'll see why in a second. So we should be able to make that type of species. We could take the carboxylic acid we could treat that carboxylic acid with LAH to reduce it, THF minus 78 degrees, followed by workup with 15% sodium hydroxide, and that would reduce the carboxylic acid all the way down to the alcohol. What we would then need to do is we would need to perform a Swern oxidation to oxidize the alcohol up to the aldehyde, and then we would need to take a Grignard reagent and perform a Grignard addition using methanol. Right, so there you have first step there is the Swern oxidation. The second step is going to be methyl magnesium bromide. The second stage of that is, of course, reacting with ammonium chloride. This would install into that molecule one of the two methyl groups. And so we would get a molecule that looks like this. We can then take that molecule and perform another Swern oxidation, followed by another equivalent of methyl magnesium bromide, followed by quenching with ammonium chloride, to then install that second methyl group. And so now we've oxidized up to the ketone, followed by addition of another equivalent of methyl magnesium bromide to generate the tertiary alcohol. Now, this particular reaction sequence is not exactly the best because it's 5 synthetic steps, all right, the LAH step being the first step, the Swern oxidation being the second, the first Grignard addition being the third, Swern oxidation is fourth, and the fifth step is the methyl Grignard addition again. This isn't the best because there's a lot of steps and we're doing a lot of functional group transformations. We're changing the oxidation state at that carbon. We're first reducing it, and then we're oxidizing it, and then we're adding it in, and then oxidizing it again, and then adding in with the nucleophile. And so this isn't exactly the best. What we could potentially do is to incorporate the Grignard addition in multiple, in a single, react it with a single carboxylic acid, and perform two successive additions. Now, before we do that, what I want to talk about is the mechanism of this reaction, because we don't know now how, so far you don't know how to make the alcohol from the carboxylic acid, what the mechanism is. So let's actually see what this mechanism looks like. So we could take LAH, as I mentioned, and react it twice to give us this alcohol, reduce the acid to the alcohol, then perform a series of oxidation and or Grignard reactions to arrive at the final product. But this would really be quite long, right? Can we think of a pathway that's much shorter that reacts with the carboxylic acid and reacts twice? Well, pathway B, what I want to do is start with the LAH reduction mechanism, and I'm just going to use a generic carbonyl. And so I'm going to say that this is either an R group or some carboxylic acid. And we're going to reduce it with LAH THF minus 78 degrees, followed by 15% sodium hydroxide. Okay, and so what we're going to get here is the alcohol. So what happens here? Well, we're going to get two successive, irreversible nucleophilic acyl substitution mechanisms. And we're going to be using hydride in this case to perform that double addition. Okay, so let's draw out the sigma aluminum hydride bond attacking the pi star CO. All right, that's going to give us a new tetrahedral intermediate. All right, so the oxygen is basically going to be bound to the aluminum. We've got a new carbon hydride bond, and then we've got this either R group or the OH. This is then going to collapse, and it's going to collapse with loss of the leaving group. All right, so you're going to get either the hydroxide leave or the alkoxide leave, and it's going to generate an aldehyde. Now, if you have two equivalents of lithium aluminum hydride in there, what can then happen is that it can react again. And sometimes you don't even need a second equivalent. You can actually just use the aluminum hydride that has that OR group attached to it as the nucleophile. So this can add in. We can generate a new oxygen aluminum bond and a new carbon hydride bond. So we still have two hydrides attached. And then, of course, we react it with 15% sodium hydroxide to give us the protonation. Right, so this gives us the alcohol. All right, so the bottom line here is that it's two successive irreversible carbonyl substitutions. And I say irreversible, and so I have to change my arrows here to indicate that this is only going in the forward direction. In that case, and also in this case down here. Okay. So the product of the first nucleophilic acyl substitution mechanism is an aldehyde, And you already know that aldehydes will react with LEH to give alcohol. So this continues, right? So the next step is also a nucleophilic addition mechanism, which will yield the primary alcohol in this case. So what this tells us is that aldehydes and ketones are more reactive than esters and carboxylic acids. So we can update our reactivity series. All right, so if we're recalling the reactivity series again, we've got the carboxylate, we've got the amide, then we've got the ester, which is about the same as the carboxylic acid. But according to the data above, we know that aldehydes and ketones are more reactive than esters or carboxylic acids, and so we can put them towards the right. We also know that sigma donation or resonance into carbonyls is going to make it less reactive, and so ketones should come first, followed by aldehydes, which are more reactive. Okay, and then we finally have the anhydrides and the acid chlorides. Okay, so now let's go back to the original question, right? Can do just that. Right, so pathway B is to start with the carboxylic acid, and the first thing we do is we undergo a Fischer esterification to give us the methyl ester. And at that point, the methyl ester can undergo 2 successive Grignard additions if we use 2 equivalents of methyl magnesium bromide, followed of course by workup with ammonium chloride. So this should give us the tertiary alcohol. So if we convert the carboxylic acid to the ester and then use 2 equivalents of methyl Grignard, we can generate the tertiary alcohol in one reaction flask after acidic workup. So the number of steps here for this synthetic sequence is 2. Right, so how would this work? Well, we're going to take this ester and we're going to undergo what's known as an irreversible addition of Grignard to the carbonyl. And so we get this tetrahedral intermediate, we got a new carbon-methyl bond, and we got the methoxide. Right, that's an irreversible reaction. And then we can get the collapse of the tetrahedral intermediate with loss of a leaving group. Right, the leaving group is going to be methoxide. And so what you're left with here is going to be the ketone plus magnesium bromide. But then we can get the second equivalent of methyl magnesium bromide to attack the carbonyl, right, via a nucleophilic addition reaction. Okay, and so that's an irreversible reaction once again. We generate the new carbon-carbon bond. Okay, magnesium can coordinate, or you can have it as an O-. And then finally, you get ammonium chloride to come in and supply that proton source to give you the tertiary alcohol. Okay, so the take-home message here is that hard nucleophiles right, can perform nucleophilic acyl substitution twice. Okay, and so the first step, right, gives you some aldehyde or ketone intermediate, but this intermediate is more reactive than the starter material, so a second nucleophilic acyl substitution occurs very rapidly, and the nucleophile is incorporated twice. So what are these hard nucleophiles? These are things like LAH, Grignard reagents, and organolithiums. Okay. Now, one more final with regard to this particular reaction is that there are two reagents, methyl lithium and phenylithium, right, will react with carboxylic acids. But they react with carboxylic acids only once. Okay, so if we have a carboxylic acid, right, and we react it with two equivalents of methyl lithium, okay, the first thing that's going to happen is that one of the methyl lithiums is going to deprotonate to give you the carboxylate. And normally we said that this carboxylate is unreactive to nucleophiles, right? It's all the way to the left in the reactivity series. The exception is with methyl lithium and phenylithium. And so the second equivalent of methyl lithium comes along and will react with the carbonyl, right? And so this is going to form a tetrahedral intermediate, which looks like this. And the reason that this intermediate forms and it doesn't collapse is that you would have loss of O2 minus, and that's not possible. And so this species is stable because what it is going to do is it's going to coordinate to the lithium cation. So you got this coordination happening, and this intermediate is stable. It just sits here until you work it up. And so when you work it up with, let's say, a proton source or ammonium chloride in a protonation step, what you're going to generate is the gem diol. And that gem diol, under acidic conditions, can, of course, react with a proton source to protonate one of the two alcohols, and you get loss of the leaving group water with collapse of that intermediate to give you a protonated ketone, which then, of course, can undergo deprotonation to give you just the regular ketone. All right? All right, so let me put methyl groups in all of these positions so that you know where that methyl group came from. That methyl group came from the two equivalents of methyl lithium. Remember that the first equivalent of methyl lithium does a deprotonation. The second equivalent of methyl lithium does the carbonyl addition. Okay, so methyl lithium and phenylithium will react with carboxylic acids only once because the tetrahedral intermediate that forms is stable. After workup, the intermediate will decompose to give you the ultimate product, the ketone, without any additional reaction because you've already consumed all of your methyl lithium and you've already protonated any excess methyl lithium that's around.